Hello everyone, in this Thierry Sicard tutorial number 34, we will review the magnetic induction experiment, the Faraday's law of induction, with a moving electric circuit which will lead to the first motor and generator, the Lorentz force with the example of the Hall effect and the example of the 1948 ampere definition. The definition of the magnetic induction is a production of an electromotive force, so a voltage, when we have a magnetic field variation. Faraday is credited of the discovery of induction in 1831, and James Maxwell mathematically described it as Faraday's law of induction. The Faraday's experiment is as follows. First of all, we find the battery invented by Volta about 30 years earlier to generate a DC current source. It is used to supply a coil A to create a magnetic field B. When both coils noted A and C do not move, no current is induced. But when one of the coils is moving compared to the other one, the coil C generates a voltage detected by the galvanometer G. Faraday's law was generalized to become the Maxwell-Faraday equation in the Maxwell theory of the electromagnetism. Of course, electromagnetic induction found many applications as inductor, transformer, electric motor, and generators. The definition of the Lorentz force is F equal Q multiplied by the vector product of V and B, where V is the electron velocity and B the magnetic field. To speak about the Lorentz force, we need first to talk about the mathematical operation of the vector product. The vector product of U by V gives a vector perpendicular to the plane formed by both vector U and V as shown on the animation. Now, if in a conductor we have a current I going to the right side, the electron will move in the opposite direction noted by the vector VE. If U vector is replaced by the vector V representing the electron velocity and V vector is replaced by the vector of magnetic field B, the vector product will be the electromagnetic field noted EM. So, in fact, the Lorentz force F is equal to the electric charge Q multiplied by the electromagnetic force EM as F equal QE. Now, if a magnetic field B is perpendicular to the electron velocity vector, the vector product of VE to B will provide an electromagnetic field EM directed to the top. This vector EM will provide a force F equal minus EM directed to the bottom. The electron going horizontally from right to left side will be pushed down and will generate a potential voltage difference called Hall voltage. The total force applied to an electric charge is the electric force plus the magnetic force called the electromagnetic force. The Lorentz force is also used for the ampere definition in 1948. The definition of the ampere is 1 amp in a two infinite conductor linear and parallel with negligible section and distant of 1 meter in the vacuum provide between those both conductors a force of 0.2 micronewton by meter. Each 1 amp current provides on the other wire a magnetic field H. We calculate H with the Ampere theorem, saying that the circulation of the vector H on a closed circuit is equal to the current crossing the area delimited by this vector circulation. Here the vector circulation is equal to 2 pi r, but as r equal 1, circulation or perimeter is 2 pi. As I equal 1 ampere, H equal 1 over 2 pi. The Lorentz force is equal to the vector product of V by B multiplied by Q, where V is the charge velocity and B the magnetic field. Q is negative because we consider only the electron-negative mobile charge. An electric charge in Coulomb is equivalent to a current multiplied by a time, as in the formula Q equal IT. Now, time multiplied by a velocity v is equivalent to a length, as v equal meter by second. So, the product t by v can be replaced by a length L. The vectorial product is I L B sinus alpha. As alpha equal 90 degrees, the force F equal I L B. As I equal 1 ampere and L equal 1 meter, the force F equal B. So, on each meter of the wire, the force F is applied. B equal mu0 H equal 1 over 2 pi, so the force equals 0.2 micronewton. On this slide, we will review both circuits to explain the generator and motor function. We will start with the generator function. The electrical closed circuit is formed with two parallel metal rails connected with a resistor on the right side and a mobile metallic rod on the left side. This electrical circuit is placed in the vertical magnetic field B directed to the top. If we move the metallic rod to the right, electric charges will have a velocity directed to the right and perpendicular to the vector B. Those moving charges in the magnetic field B will create an electromagnetic field EM, and so a force QEM. Of course, the force QEM will have an effect only on the free moving charges like the electrons. As by definition the conventional current is in opposite direction of the electrons, a current will pass as shown in red. Until now, we could create a DC current only with a Volta battery. Somehow, we create a new mechanical generator able to produce a DC current if the metallic rod is moved linearly in a magnetic field. Now we will see the motor function. We have exactly the same circuit with two parallel and metallic rails with a moving metallic rod, but this one on the right side is connected to a voltage source in series with a switch in open position. When we will close the switch, a current will be forced in the circuit. In the metallic moving rod, the blue arrow represents the direction of the negative charges and the red arrow represents the conventional current direction. As the electrons will have a velocity in the metallic moving rod, the vector product between the electron velocity and the magnetic field will provide a magnetic force F equal at QEM, directed to the right. As this force is applied to a negative charges, the electrons, the mobile rod will be subjected to a force in the left direction. As the metallic rod is mobile, the rod will roll to the left side. We created a motor which is able to move a mechanical part. If we compare now the generator on top and the motor on the bottom, we can say that for the generator we applied a force Fm to the right direction and we provided a current directed to the bottom. For the motor, we did the opposite. We applied a current directed to the bottom with a source voltage and we created a force directed to the left, which means in the opposite direction than the generator. This means that in the generator operation, we move the mobile rod to the right, but this move generates another force in opposite direction. So this means free energy does not exist. I want to thank you for your attention. On my next Thierry Sicard tutorial number 35, we will talk about the first mechanical electric generator and a summary of the electricity discovery through the main famous contributor Coulomb, Volta, Ampere and Faraday, which gave the main electricity unit, the electric charge, the Coulomb, the voltage unit, the volt, the current unit, the ampere, and the capacitor unit, the farad. So see you soon and stay tuned.